guys. Sorry for being a little bit late. It had me update my board that I use for writing right before. So it was all of a sudden out of date. So we will go ahead and get started. Again, sorry that I'm a few minutes late, but let's go ahead and start reviewing. I will again I will go ahead and start answering the questions that some of you guys have posted. I have my big binder of all my materials. So I will start going through those. So I'm going to start with Daniel's question, which had to do with our final. So not our final, our Unit 4 test. So let me grab that test. And he wanted number 27, A and B. Okay. So let's go ahead and look at number 27. This is from our Unit 4 test. Hold on, let me adjust a couple things on my end really fast. And if you guys could give me a minute, and until I kind of get caught up, don't comment too much more in the comment section because it's going to have me keep scrolling back and forth. Okay, so let's go ahead and do, this is our Unit 4 test. And we are looking at number 27. Let me change this. This is a little too thick for me. All right. So what this problem says is it says gallium has an atomic number of 31, and it exists as gallium-69 with a mass of 68.9256 AMUs, and then gallium-71, and that is 70.9247 AMUs. And what we want to do is we want to find the abundance of each isotope. So in this problem, what you want to do is you want to figure out the percent. So if we were to calculate this, we know that our equation for our isotope is the sum of, so that's our equation for the sum of, and this is our mass, or our isotopic mass, times our percent abundance. Whoops, let me go back. And so I really don't like the size of this, and that one's a little bit too thick. Oh well. All right. So what we know is we know that we have gallium-69, and it has a mass of 68.9256. What we don't know is we don't know the percent abundance, so we're going to call that X. And then we have gallium-71, and we know that mass to be 70.9247, and we're going to call that 1 minus X. Because again, these two should add up to 1. So if this is X, 1 minus X would be what this one is equal to. And then we do know if we look at our periodic table, and I think that's the one thing I don't have in front of me. Let me see if I can find my periodic table. You know, I don't think I have the periodic table that I gave you guys actually in front of me. Give me a minute. I might not have that one at all, actually. I'm going to look on a different periodic table. So if I look at a periodic table and I look at gallium, what I see is that gallium has a total atomic mass of 69.723, and this is AMUs. So if I were to create this equation, what I would do is I would say that my total mass, 69.723 AMUs, is equal to 68.9256 times X plus 70.9247 times 1 minus X. What you want to make sure is over here is that you distribute that and then you solve for X. So what you end up getting, and again, I told you guys that I was kind of going to be going through some of these problems a little bit faster so I can make sure that I get through all the questions. There is definitely a lot of material to cover. So again, I'm not going to go through all the math in this, but this is the equation that you would solve. And what you would get is you would get X to be 0.603. And if you change that into a decimal, that'd be 60.3%. And then you have 1 minus X would equal 0.397, and that would be 39.7%. And so that would be your, again, this would be gallium 69, and this would be gallium 71. So those would be your two percentages. And so if you go ahead and you look at part B, what it says is it wants you to sketch the spectrometer. So this would be intensity, and this would be your mass. So remember, the mass increases as we go across. So the first one that we're going to draw is the 69. Now, the intensity, the tallest peak is always 100% intense, or at 100. So if this was my 100, my first peak, the one that has the greatest abundance, is going to be the tallest peak. This is a little bit more than half. So if this is my peak for gallium 69, my peak for gallium 71 is going to be somewhere over here. Now, that's all I wanted to show, but the fact that it was the tallest peak, that it's the first one and things like that, that's what you want to make sure that you do for that problem. So that is that math problem. Specific heats conceptually. When we talk about specific heats, I'm going to look at a couple different problems. Let me find them. Give me 1 minute. All right. Okay, so looking at specific heats conceptually. So specific heats. So the specific heat is represented in joules, grams, times degrees Celsius, or it could also be represented in calories, grams, times degrees Celsius. And what this tells us is how easy or how difficult it is to change the temperature of a substance. If this number is really large, that means that it's going to be very challenging to change the temperature of a substance, or it's going to require a lot more heat, where if the number is really small, it's going to be a lot easier. So when I talk about understanding these conceptually, what you want to think about is if we had two different specific heats. So let's say that we have silver, and it has a specific heat of 0.233 joules, grams, times degrees Celsius. And we have sodium, and it has a specific heat of 1.20 joules, grams, times degrees Celsius. I'm going to see if I could type something out really fast so I don't have to, let's see, type, equation, and I'm not seeing it. Oh well. And so if we have these two values, and let's say we had a problem that says 40 grams of each metal were originally at 20 degrees Celsius and were placed on a stove for the same amount of time. So they both start at 20 degrees Celsius. So Ti equals 20 degrees. They were both placed on a stove. They both have a mass of 40 grams, and they were both placed on a stove for 20 minutes. What that means if they were both placed on the stove for 20 minutes is that they both absorb the same amount of heat. And so it says which one will have a higher temperature when they're taken out. Well, the one that's going to have the highest temperature is going to be silver because it's going to take less heat to change this 1% or to change this 1 degree Celsius. So if I were to say add 100 joules of heat to both of these substances, my final temperature for silver is going to be a lot higher than my final temperature for sodium because sodium is going to need more temperature to change, to increase in temperature. So that's what the problem means when it says think about these conceptually, is how would these affect, not necessarily mathematically, but how could we think about these specific heats? Can you briefly explain how valence electrons and highest energy level shells are similar and different, and why? I think I'm a little bit confused. Okay, briefly explain how valence and electrons and highest energy level shells are similar and different, and why? Alicia, I think I'm a little bit confused by that question. But I will explain it to what I believe maybe you're trying to get at. So let's talk about valence electrons. So valence electrons are usually defined as those electrons that are in the highest energy orbital. So when we think about that, usually what we're talking about is at the highest energy S and P orbitals. And so if we were to write an electron configuration, let's say that we write an electron configuration for, let me grab my periodic table again. Let's say that we write an electron configuration for fluorine, which has 9 electrons. And so that would be, 1s2, 2s2, 2p5. Don't forget that when we're looking at the electrons, these numbers should add up to the total number of electrons that are in this atom. So these numbers should add up to this. Now, if I were to rewrite this in noble gas configuration, I look at my previous noble gas, and this would be helium, and then I would have 2s2, 2p5. If I look here, what I see is that the highest energy level that's being filled is the second energy level, and I see that I have 2 plus 5, I have 7 valence electrons. I could do the same thing, let's say, with something like, I believe that's germanium. So let's see germanium. If I were to write out this electron configuration, this is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 6, 4s2, 3d10, and then 4p2. If I were to rewrite this as my noble gas configuration, my previous noble gas is argon, and I see this as being 4s2, 3d10, 4p4. If I look again at my highest levels, I'm looking at my 4s right there, and what I see is that I have 2 and 4. So what I see is that I have, again, 6, excuse me, this should not be 4, this should be 2. Sorry, you guys. And so what I see is I have 4 valence electrons. So again, I'm looking at the S and P, or the highest numbers, and if I add those together, I can calculate how many valence electrons I have. Try hard. Can we go over number 4 on worksheet 1.4 on density? That's unit 1, density worksheet 1.4, number 4. For number 4, I really can't go over because I cannot show that graph. But the idea with that is that you have a graph and you want to be able to graph the densities of a couple different elements. When you graph the densities of those elements, what you want to remember is that the density is equal to the slope. So using the density, I can use the slope to create those graphs. And so that's what part A says. Part B, we want to find the volume of let's see. We have a 1 inch cubed. And if I were to do that, what it means is I'm going to have 1 inch cubed. And if I were to multiply this by 2.54 centimeters, if I were to take the cube of that and divide this by 1 inch cubed, so I'm going to cube root that. That's going to end up being 16.387 centimeters cubed. And then, whoops, I want to remember that 1 centimeter cubed equals 1 milliliter. So in this problem, what we were doing is that we were converting inches cubed into milliliters. And what we end up getting is that this is equal to 16.4 milliliters. Once you were given this 16.4 milliliters, it asks you to find the mass of your 1 inch cube blocks. So this right here is equal to 1 inch cubed. So this is a conversion factor. So if I knew, for example, for tungsten, if I knew that my density was 19.60 grams per milliliter, and it wanted me to figure out per inch cubed, I can multiply this by 16.4 milliliters over 1 inch cubed. Notice that my milliliters cancels out. And if I multiply this, I get 321 grams per milliliter. And so that's what it was asking you to do. It was asking you to create this conversion and then use this conversion. Oops, I put milliliters and I meant to put, that's not milliliters cubed. That is inches cubed. And it wanted you to use that to convert this grams per milliliters into milliliters, into grams per inches cubed. And so that's what you were doing for those problems. And again, I can't show the graph just because of the way that the setup is. So hopefully that kind of makes sense for that problem. The big idea is that you were using dimensional analysis and you're also using density as a conversion of dimensional analysis. Okay, number 23 on the Unit 5 tests. And you know what? I don't know if I have that one in front of me. Give me a minute because I might have left the Unit 5 test at school. Okay, here it is. Can you do 23D on the Unit 5 test? Okay, for 23D, there was 2 answers that I accepted. So the first thing is you wanted to know that we were talking about tungsten. And if you were to write the shorthand of tungsten, 6s2, 4f14, 5d4. And we wanted to get to tungsten with a 6+ charge. That means that we lost 6 electrons. What we see is that we need to remove 6 electrons. Now, there were 2 answers that I accepted. I first accepted that you lost your 6 electrons from this orbital and from this orbital. So the first one that I accepted was having xenon 4f14. I then also accepted losing them from these 2 orbitals. So going in order right here. So you could have also put xenon 6s2 and then 4f12. So again, however you lost those electrons, whether it was these 2 or going in order in the way that you wrote it, I accepted either ones of those. Any other ones I did not accept. Now, I know that kind of sounds confusing, and there's a reason why it really could kind of be either one of these. But as long as you know that you can either lose them in order or from these 2 orbitals, but you can't lose them directly from the 4f only. So I did accept both of those answers. Can you explain how to know which element is greater or lesser when looking at trends like atomic radius and electron affinity, when looking at elements who do not share the same period or family? Oh, what you want to do for that. So if you're thinking about elements that are not in the same period or family, what you want to remember is that you have 2 trends that you're looking at. You could either have, if you're going across a family, or excuse me, if you're going across a period, what you're looking at is the number of protons. So the charge. If you're going down a family, what you're looking at is distance from the nucleus. These both, if we increase the charge, that's going to increase our Coulombic attraction. If we increase the distance, it's going to decrease our Coulombic attraction. One of these actually wins out. And the one that wins out is always distance. So moving down a family is always going to win out in the trend. The further out they are, the decrease in the energy or the Coulombic attraction is way greater than any other trend up here. So the trend down always wins out versus the trend across. I hope that kind of answers your question for that one. And again, I am moving through these pretty quickly because I want to try and cover as many topics as possible. Will there be any more challenging problems like on 1.3, or will they be more straightforward? You guys, I'm not going to answer questions of exactly what's going to be on there. You want to know about things that we have covered. I can cover that problem on worksheet 1.3, so I can cover that. But again, I'm not going to say what exactly is going to be on there or not. 1.3. D. Okay. So let's go ahead and look at that problem. So we are now looking at some dimensional analysis. And I kind of already went over a cubed root problem when I was looking at worksheet at that dimensional density one. But let's say that we wanted to put 22.4 liters and we wanted to convert that into centimeters cubed. So what we're going to do is we know that we can convert liters into milliliters. And we also know that we can convert milliliters into cubic centimeters. And actually, this one doesn't even involve a cube. So, so what we would do is that we would have 22.4 liters. And I know that 10, whoops, not 10. Sorry, let me erase that. I know that 10 to the negative third liters is 1 milliliter. And I also know the conversion that 1 milliliter is 1 cubic centimeter. This is something that you guys should know. This is something that we've talked about, especially when we talked about density. So notice that our units cancel out. All I need to do is divide this by 10 to the negative 3. And what I get is 22,400 cubic centimeters. If I wanted to do one that actually had cubed roots, what I would do is I would look at trying to find one. I guess P would be the best example. So this was D. P says convert 0.28 grams per centimeter cubed. And I'm going to show this another way just in case. And I want to convert this into grams per meter cubed. So there is another way to look at this problem. So I'm going to show you guys this way. So 0.28 grams per 1 centimeter cubed. And I want to convert my centimeters into meters. I have a conversion that I know. I do know that 1 centimeter is equal to 10 to the negative 2 meters. So what I can do is if I want to convert this into meters cubed, I need to have 3 centimeters. So what I'm going to do is I'm going to have centimeters equals 10 to the negative 2 meters times 1 centimeter over 10 to the negative 2 meters times 1 centimeter over 10 to the negative 2 meters. Notice that I have 3 centimeters multiplied together. So those all cancel out with this 1 centimeter right here. And if I multiply all of these meters together, I will get meters cubed. So really what I'm doing is I'm taking this 0.28 grams and I'm dividing it by 10 to the negative 2, divided by 10 to the negative 2, divided by 10 to the negative 2. And if I were to plug that into my calculator, I would get 280,000 grams per meter cubed. Wait, is that, yeah. That makes sense. Seems like a big number. But that's how the math works out. Okay, so that would be our problem. Okay, let's go ahead and move on. Can we do an example with the half-life formula? Okay, let's look at half-life. I will probably only be able to get through the last things that people wrote down. So just so you guys know, I probably won't be able to get through too much more than what's already on the list. So you guys can try to add more, but again, I won't be able to get through too much more. Just looking at time. Half-life. Give me a minute. I'm trying to find a problem. All right. Let's say that we have a problem. Let's say that, sorry, let me turn this off. Not quite what I wanted to do. Okay, let's just say that we have this one. So let's say that we have a 64-gram sample. Decays to 2 grams after 40 days. What is my half-life? So I'm looking for half-life. First thing that I would do when you're solving this problem is make sure that you can or cannot do it the easy way. So let's say that we have 64 grams. After one half-life, we're going to have 32 grams. After another half-life, we're going to have 16 grams. After another half-life, we're going to have 8 grams. After another one, we're going to have 4. And after another one, we're going to have 2. So notice that it is a nice even amount. So here's 1, 2, 3, 4, 5 half-lives have passed in order for the substance to decay. So if we have 40 days that have passed total, I can divide this by 5. And what I will get is that each half-life is 8 days. And so again, that's T to the 1/2. So that would be my half-life for that sample. I would say that if you wanted to look at more complicated problems, I would definitely go back to my videos and I would look at our review for Unit 4 because I did do a couple half-life problems that involve some more complicated math. I don't want to spend a whole lot of time doing a big problem with half-life just because of our time crunch. So again, this is kind of the basis. Remember, half-life is the time that it takes for half a substance to decay or to radioactively decay. So this is my original substance, 64 grams. It would take 5 half-lives to decay into 2 grams. And then I would get my half-life to be 8 days. And again, go back to the Unit 4 video. I did a couple problems, I believe, in that video that went over more details. So go back and watch that. Can we talk about the comparison, the strength of particles with the heat of fusion given? When we talk about heat of fusion, I'm just going to talk us through this one because there's really not much I can write down. But when we talk about, wait a second. Can you go over how to do 2 or 3 step problems mentioned on the final review? I'm not sure what you meant by 2 or 3 step problems. You need to be a little bit more specific what you mean by that, Molly. So if you can type that out, I will answer that. Comparing the strength of attraction between molecules and the heat of fusion given. The heat of fusion is how much energy it takes to either melt or, well, yeah, to turn a substance from a solid to a liquid, or we can talk about liquid to a solid. When that heat of fusion is larger, so if it's a larger number, what that means is that those particles have a strong attraction to each other, and more energy is going to be required to turn those substances or to weaken that attraction and turn them into a liquid. So the stronger that attraction is between molecules of a solid, the higher the heat of fusion is because it's going to take more energy to turn them into a liquid. Same thing with heat of vaporization. The higher that value is, for the heat of vaporization, the stronger those molecules are. So to turn that substance from a liquid to a gas is going to take more energy if that heat of vaporization is larger. If that heat of vaporization is smaller, that attraction between those particles isn't as strong, so not as much energy is required to perform that phase change. Number 3 on worksheet 5.1. Let me see if I can find that. Oh, Alicia, the one with the moles, don't worry about the moles. I talked about that in class that you didn't need to do that one. So really the only thing you need to be able to do on worksheet 5.1 number 3 is being able to calculate the nanometers and convert that into energy. So don't worry about the moles. That's nothing that we have really gone over. So you're not going to need to know about that one. Should we memorize all the prefixes and scales from the first unit, or should we just have those 3 that we starred ages ago? You should have some of the basic ones. You should have kilo, you should have centi, you should have milli, and also we recently added in our last unit nano. So you should know those 4 for sure. Again, that's kilo, centi, milli, and nano. Those are the most common ones and the ones that you will need to know. If there was something else on the test or quiz, I would definitely give those to you. Jordan, are there any other important constants that we should know other than C, H, and R? I don't believe so. Those sound like the constants that we have covered so far. Can you go over successive ionization energy and how to determine an unknown element's valence electrons based off of that? Molly, can you give me an example of a problem for that? I have a hard time kind of sometimes answering some of these questions without a problem. So if you have a problem or something that you're looking at that I can go off of, that would be really helpful. So again, so I can talk about some topics, but it's a lot easier for me to talk about topics if you guys are suggesting some problems. So if you guys have some problems to suggest, go ahead and type those up and I will look them up. So if you guys want to suggest some other things, go ahead and leave that in the comment bar. Number 20 on Unit 1 test. All right, let's go ahead and look at Unit 1. Unit test. Let me try to find the Unit 1 test for some reason. Oh, here it is. Okay. Number 20. Number 20 on the Unit 1 test, I'm guessing that is the multiple choice question that you're asking about. So what it says is that we have a 1 liter sample of carbon dioxide gas. Does that sound right? Hopefully that's the one that you guys are thinking of. So this is Unit 1 test. Number 20. It's a multiple choice question. We have a 1 liter sample of carbon dioxide that has a mass of 2 grams. So we have 1.0 liters. It has a mass of 2.0 grams. This is carbon dioxide that it says that it is. And then it says we also have a 1.0 liter sample of 0.7 grams, and this is of methane. Kind of jotting this down. If both samples have the same number of particles, so we can say, let's just give it a number. It doesn't matter. Let's just say they each are composed of 3.0 particles. It really does not matter. So we'll say that they're both have 3 particles. Why not? Which of the following may explain the difference in mass? So again, they have the same volume. They have the same number of particles. So what is happening? So if we look at these problems, as carbon dioxide particle is larger in size than the methane particle. So if our carbon dioxide particle is larger, so let's say that it's this size instead of this size, is that going to take into consideration our differences in mass? Let's just go on and look at the other ones. The carbon dioxide particles are closer together than the methane particles. Okay, so if they're closer together, maybe they're going to look something like this compared to maybe a little bit more spread out, which means that our density would be different. The carbon dioxide particles are moving faster than the methane particles. So we're talking about speed. Now, again, speed isn't going to have anything to do with this. Speed only has to do with temperature. So this isn't dealing with temperature at this point. So that's not going to have an effect on this. And then it says the mass of carbon dioxide is larger. So these particles could be the same size, but one's going to be more massive. So even though this right here may be larger than methane, that's not going to necessarily depict mass. Size of the particles does not necessarily mean the same as mass. Okay? Now, these particles could be spaced differently, but if they were spaced differently, that might not necessarily take into consideration their mass. So really, the only correct answer is D, where it says that the mass of carbon dioxide particle is larger than that of methane. Thus, if we were to look at this, if we were to kind of think about each of these 3 particles, well, they would each have 0.75 grams, where maybe these ones were a little bit less, about 0.23 grams. So notice that the only thing that would really account for the difference in this mass would be the difference in the mass of each particle. So hopefully that answers that question. Could we do 23C on unit test number 2? Unit test number 2, 23C. Okay, 23C. Number 23C, it says, find the volume of gas if the conditions were adjusted to STP. So when you're doing this problem, we have some initial conditions and we have some final conditions. And we could talk about things like volume, pressure, the number of moles, and we could talk about temperature. So in the original problem, we have some values, and we'll call these our initial values. So for example, we were told that the original pressure was 84 kilopascals. So I'm going to put this right here, 84 kPa. We were told that we had a temperature of 12 degrees Celsius. And then we were also told that we had a volume of 0.60 liters. So we were told that our volume then adjusts to, sorry, just trying to find one thing. We were told that our volume adjusted to STP. What you want to remember is what STP is equal to. STP is standard temperature and pressure. That's defined as 1 atmosphere or 0 degrees Celsius. What we need to be able to do is then convert this into pressure of kPas and temperature. And we're going to convert both of these temperatures into kelvins. So if it's adjusted to 0 degrees Celsius, this is also the same as 273 kelvins. 1 ATP, you should know your conversions. This is 101.325 kPa is the same as 1 atmosphere. And so what we're asked to find is this volume right here. 273, so if we were to add 273, this is going to be 285 kelvins is going to be my other temperature. So what we see is that we have volume, pressure, and temperature, and we need to be able to isolate our volume final. The only equation that we have that has all three of these variables, notice that the number of moles is not changing or is not referenced, so we're going to assume that it's not changing. So we have this equation, P1 V1 over T1 equals P2 V2 over T2. So what I'm trying to solve for is my V2. Now I'm going to isolate my V2, and to do that, I'm going to multiply by T2 to get T2 away from there, and then I'm going to divide by P2. So these cancel out, and then I'm going to have T2 over here over P2. So here I get that my second volume is equal to T2 P1 V1 divided by P2 times T1. Amina, yes, ideal gas law does have to be in atmosphere. So you want to make sure that you're always converting those because, again, R has those units. So let's go ahead and start plugging things in. We get 273 kelvins. Whoops, I don't know why that did that. 273 kelvins times my original pressure, which is 84 kilopascals, times 0.60 liters. And then we're going to divide that by my second pressure, which is 101.325 kilopascals times 285 kelvins. So units cancel out, units cancel out. I'm left with liters. And so that would be correct. So I'm trying to find my final liters. Let me go ahead and calculate this because I don't have the answer right in front of me. 273 times 84 times 0.6. I'm going to divide that by 101.325. And then divide that by 285. And I get, if my pressure increases and my volume decreased, and my temperature increased, I get my new volume to be, with two significant figures, 0.48 liters. So that would be my new volume. Let me just double check. 273 times 84 times 0.6. And I'm going to divide that by 101.325 and divide that by 285. Whoops. Yep, so 0.48 liters. That would be your final answer for that. Number 1D on the Unit 2 gas laws homework. Number 1D on the Unit 2 gas laws homework. Gas homework. Just trying to find that homework sheet. I have the answers, but I can't find the homework sheet. All right, let's go ahead and just do this from what I have. Okay, so let's look at 1D on the Unit 2. 1D. This is a combined gas law problem. I'm not going to do another combined gas law problem. So look at the last one. that we just went over, because that was a combined gas law problem. That's the same thing as the 1D. You just need to make sure that you are, instead of solving for volume, this time you're solving for P2. So in 1D, that's an ideal gas law problem. Let's go ahead and look at B on the ideal gas law homework. So let's say that we had, so we want how many moles? Of oxygen will occupy a volume of 2.50 liters at 1.20 atmospheres and 25 degrees Celsius. So we're given some information here. As we can see, we are given the volume equals 2.50 liters. We are given that we have a pressure that equals 1.20 atmospheres, and we are told that our temperature equals 25 degrees Celsius. And if we were to convert that into kelvins, we get 298 kelvins. So notice that we don't have a before or after. So there's no like change in volume or change in pressure. We're talking about one point in time. And so this is where we use our equation PV equals N RT, and R is a constant. In this equation, they're asking us to solve for the number of moles. So I'm going to divide both sides by R and T. Those cancel out. And I can start plugging things in. So I'm told that my pressure is 1.20 atmospheres. My volume is 2.50 liters. R, this is our constant, 0.0821 liters times atmospheres divided by moles times a Kelvin. And then 298 Kelvin. So notice that my Kelvins cancel out, atmospheres cancel out, liters cancel out. And so what I'm left with is my moles. And if I calculate that out, I get 0.123 moles. For the next problem, oh, it just is another PV equals nRT. So there's that problem. You definitely want to know your gas laws, so make sure that you guys review those. Ideal gas law. For the laws relating pressure, temperature, and volume, do they have to have specific units? Aiden, no. For that law, so for the combined gas law problem, you don't need to have specific units, but you want to make sure that your units match. So if we look at the previous page that I was just doing, let me go back. So what you notice on this problem is that I did choose my pressure temperatures to be the same. So I knew that STP was 1 atmosphere. I don't want to plug in 1 atmosphere when this is kPa. It does not matter if you could have converted this into atmospheres. I decided not to. I just kept them both at kPa, but you could have done either or. So you just want to make sure that your units before and your units after match, or that your units cancel out, but they could be whatever they need to be. You could have, instead of liters, you could have had milliliters. It really doesn't matter. So as long as your units are the same, and yes, you want to make sure that whoops, hold on one second. You always want to make sure that this is not working. There you go. You always want to make sure that your temperature is in kelvins. I have time for maybe one more quick problem or one more quick idea. If you guys have something that you're dying to ask, one more. you definitely want to make sure that, again, you review all your old tests and quizzes, ask questions. I will be in class tomorrow a little bit early, but I have to go make some copies before the class period, so I will be in and out. So if you guys are finished reviewing tonight and you're like, wait, I have like one more question I just am dying to ask, I will have probably a few minutes before second period. So don't forget that second period, that bell rings at 8 o'clock. So we're going to be starting our final right at 8. I want to make sure that I give you guys as much time as possible to take the test. So I will not be answering questions once the bell rings. We're going to come in, and you guys are pretty much going to start your test right away. It's 90 multiple choice problems. It does not mean that there's no math. It just means that the math is a multiple choice problem. So I want to make sure that I give you guys as much time as possible. All right. So I think that we are good. If you guys are dying to ask me one more question before tomorrow, Daniel, I really can't have you guys do that because it wouldn't be fair to other students who don't have that time. So you guys have the 2 hours, and that's really it. So you want to make sure that you use your time wisely. I can't really let you guys go later when I don't allow other classes to go later. Okay, so have a great evening. I hope you guys study. Make sure you guys create a good 3x5 card. Put everything you need on there. And I will see second period bright and early tomorrow. And for sixth period, I will see you guys on Wednesday. Have a great rest of your day, you guys. All right, great rest of your evening.